Today I'm going to be talking about Lab 2, the motion of a falling object. The problem was to create a computational model for a falling object and compare it to the experimental data. The result was a computational model with gravity and drag force approximates the motion of a falling object better than the model with gravity alone. Here is my video. Here is a paper ball falling from a known height. I uploaded that video to Tracker, set some constraints, and I set the axes to where the ball was dropped. Right here, I also found the point mass of each of the ball. From the tracker data, I uploaded it to Python and created a computational model. The first thing I changed was the ball's mass, which is 4.54 grams, which is converted to 0.00454 kilograms because it's SI units and we need SI units. I also changed the ball's position to be vector 0, 0, 0. That is because at time 0 from the tracker, the y coordinate position was 0. And we only consider the y-coordinate because theoretically it should drop in a straight line. The ball's initial velocity was set to 0, meters per second because it was dropped from rest, and time was set to 0. Delta t was set to 0.01 to make accurate predictions. The magnitude for weight force was set to 9.8 meters per second squared. The unit vector for the y-axis was chosen for the up as the up as the direction of the positive y-axis, so j hat was set to 0, 1, 0. The constant b should be ignored because that is the model discussed in lecture video. The constant a is the magnitude for the turbulent force, and that is what we used for this video and this lab. I set a to 0 when I was only considering gravity, and set a to 0.00332 when I was considering gravity and turbulent drag force. In the loop is where Newton's second law comes into play. I set time to 0.625. Actually, I set time less than 0.625 because that is when tracker's data ended. I set weight equal to ball's mass times the gravity constant times the negative j hat unit vector. Fd should be ignored because that is the drag force equation from the lecture videos. Ft is the force for turbulent drag force, and it is a times square of the ball's velocity. Fnet is the combination of all forces, which in this case is the weight force and the turbulent force, drag force. Ball's velocity is determined from Newton's second law, which is final velocity equals initial velocity plus Fnet over ball mass times delta t, and the ball's position is determined from ball's position plus ball's velocity times delta t, and ball velocity is found in the previous line. T was also set to previous time count plus delta t. The arrows are used for the computational models to show the forces. Now we'll run the code. As you can see, the yellow represented the weight force and the blue represented the drag force. The drag force increased over time while the yellow weight force remained the same. Next, I took this data and made it into an Excel spreadsheet. The blue is the experimental data, the green is the position versus time for the weight force alone, and the red is the position versus time for both the drag and the weight force. As you can see, initially they were all about the same, but as drag came into play, the model for only weight force had a huge discrepancy. The model for drag and weight force was much better in predicting the position. There's a slight discrepancy in the middle, and that could be due to the miscalculation of where actually the center of mass was, because it was blurry, and because the ball did not drop in a straight line, as can see by the origin and the center of mass positions. Let's consider this what does it mean question. Which model, if any, predicts a terminal velocity? Well, let's know what terminal velocity is first. Terminal velocity is when the force of gravity on an object equals the resistance to its movement through a fluid, which in this case is air. When an object falls, gravity causes it to accelerate. Eventually, the force of the air resistance on that object will equal the force of gravity. When the two forces are equal, they will cancel out, and therefore the net force will equal 0, which also means that there is no acceleration. The object will move at a constant velocity, and this velocity is referred to as the terminal velocity. And since in order to get a net force of 0, the model with drag force and gravity would best predict a terminal velocity. Let's consider this what-if question. Imagine the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where this object was initially dropped from rest? Let's make some assumptions first. The first assumption is that there are still only two forces acting on the object, the weight force and the drag force. The second assumption is that weight force will be the same and the drag force is only a function of velocity. And the third assumption is that density of the air is constant throughout. So, the net force is only 0 for one value of v. Therefore, terminal velocity is not influenced by initial velocity. Also, terminal velocity will only be reached faster unless it was thrown faster than the terminal velocity. Then in that case, it depends on how much faster the terminal velocity was. So the initial velocity of the object has no influence on the terminal velocity. Thank you. That's the end of my video.